Looks like it is recording. Can we get started?
We were good to go. I was presenting first.
Okay. Can you all hear me now?
Yes.
Yes.
Can we get started?
Yeah.
Please.
Okay, awesome. So looks like let me make sure that we go through this logistics. So we are on an exception three, and I'll be going first. And then my discussant is Raj. So basically, Raj will be asking questions about the presentation that I'm doing. Similarly, others has their own discussions, right?
I'm
Perfect.
sorry, but I was not
Yeah.
assigned one. I apologize. I had to make a last minute change
Oh,
for today's meeting.
oh, no worries, David. I saw you joined late, right? No worries. So one of us can ask the questions if that's okay.
Okay. Absolutely. Thank you.
All right. So let me start. My presentation is AI agents transforming higher education. So I have a little bit of context and background. So my professional experience is building integrations for higher education student information systems. So when I say student information system or higher education SAS, just to be a little clear on that, so basically that's different portals that the higher education university students will log into at different point in their school time. Like for example, enrollment, scheduling, performance tracking. There are many different functions within the universities where the student will engage, right? So basically, the goal here is to come up with an agent with a personalized support and generate actionable insights, which in turn will provide better analytics, which isn't there today. And then from a market stand perspective, as with any industry, even for higher education or educational tools perspective, there is a rapid growth projected for the next 5 to 6 years. So that's the precursor. And then why current models struggle with student data? Student data is a little bit tricky compared to different verticals. Every other vertical has their own challenges, but specifically for student data or educational data, the sampling and the behavioral concepts are slightly tricky. And the institutions lack robust technical methods for improving that data quality within the different portals of their student information system. And the risk without proper augmentation, models face challenges with respect to imbalances and fairness with respect to prediction, which is one of the core struggles. And random time warping mix-up is an augmentation technique, which I believe will help with this gap or closing the gap when it comes to student information system. Right? This technical method basically is designed explicitly for handling the time series data. When I say time series data, so what exactly it means is basically at different students will have their own the data that's locked for the student is pretty much time series in the sense that the activity logs varies from whenever they sign into a different portal, they go to like the parking permit store, they go to different areas within the school ecosystem, and the records are pretty much static at that point in time. With this RTWM method, what's going to happen is I'll talk more on the next slide, but basically the workflow is more like capturing the entire log for every single student. So we are able to simulate the natural variations within those engagements.
So sorry, David.
Is it just me or
Yeah,
I
Satish,
cannot
your
see
screen.
Satish? Yeah.
Oh, what happened?
Your
We
screen
cannot
is
see your screen, Satish.
share your screen. It's not shared yet. The content.
I thought I did share.
Yep, coming up now.
Oh, I'm sorry. Do you want me to go back again and walk through the
No,
slides
it's
real
fine.
quick?
Nope, nope.
I was following with your words, so I'm happy where we are.
Yeah.
Okay. Awesome. Yeah, so I'm on slide three. You guys can clearly see it now, right?
Yeah.
Okay, awesome. Thanks, everyone. So, from a technical workflow standpoint, basically, like I mentioned in the last few seconds, the data is the most important aspect. With this time warping, the first step is basically to stretch the data and in some cases compress along the time axis. It's to mimic the student phase through the entire journey. And with step two, basically mixing up the augmentation. So the linearity comes into play, and it actually combines the features and labels from multiple students. So the end result is basically creating a synthetic example that smooth out the decision boundaries and reduce overfitting. It's kind of a very high level technical overflow, but with a few minutes, we can go deeper. But unfortunately, that's basically creating the synthetic example. And now, with this experimental design, what I was able to do is kind of simulating the real institution log. Like, for example, I picked attendance, engagement, and few activity records. And then what I did is basically compare the baseline. So I started with without augmentation, and then I started with jittering and scaling, which is kind of the standard augmentation method. And then the third is basically the whatever the proposed method with the real-time warping method, I was able to validate the approach. The key metrics that I tried to capture was classification accuracy, robustness to noise, and the subgroup fairness. So, based on whatever I was able to validate with this method, it clearly outperformed the standard methods. These are some of the metrics that I was able to capture. So the accuracy improved from 78% to 88% when it comes to compared to the no augmentation method with the RTW. Similarly, when it comes to robustness, I was able to achieve a high rating for the resilience as well. As far as the comparison, it consistently beat both standard as well as standard jittering and the scaling techniques. Okay. So another important aspect of this journey is the equity gap. And what I mean by that is the accuracy has to be the accuracy has to be measured across different subgroups. Like when I say different subgroups, there are multiple student groups within the higher education ecosystem. Like for example, some may be specific to some of the what do we call it? Specific subgroup, such as, let's say, if the journey for that particular week is going to be attending few classes and going to the parking permit or paying the tuition balances, that's one subgroup that I classified. Similarly, let's say if there is another scrubbook where they focus this particular week or the next couple of weeks, whatever it is, specifically on a project. And there are multiple scenarios, but the bottom line is I was trying to get the metric based on the accuracies. And the baseline gap is basically for non-augmented models showed 6.5% gap in the accuracy. Whereas with this time series, I was able to reduce the fairness gap to just 3%, ensuring more equitable predictions. Conclusion, this is, at least from my perspective, since I had experience with this student information system integration, this RTWM experimentation was pretty cool to me because I was able to like effectively see what it can bring to the education sector. And I believe it directly supports the institution goals for student retention and success. Basically, it all comes down to the predictive analysis that I was able to measure throughout this journey. That's pretty much what I have, and I'll stop here for any questions.
So yeah, Satish, this is Raj. I wanted to first, thank you for walking us through this. Looked awesome. So the main objective is you're trying to create a better predictive, capability in the education platforms.
Correct.
And the technique you used, like using synthetic data, you have, you have your models are performing better than LSTMs, which are
Correct.
like the time series
Correct.
standard. forecasting options.
That's right.
And then the data set, how have you, like, where was the starting point of the data sets? I mean, did you use open source or?
No, so what I did was I actually created, so I know what kind of like, we cannot use the real student data for the experimentation. So what I did was I was able to create a data set by, like, I kind of know, like, for example, let's say if I need to capture student data for attendance system, like I know that the student ID is critical, and then the student name, and then the class, and then the dorm or wherever the class is happening, as well as whenever the student clocks in and clocks out. So I kind of know the data structure. So what I did was in my Python program, I created the data set in real time by populating some of these on my own, which kind of mimics what is really out there.
Got it. Thank you. I think those were my questions. Thank you for the presentation.
Awesome. Yeah. Thank you, Raj. All right. So let's see who's next. Malek. Malek, I will.
Yes, you will make me presenter.
You can, I think you should be able to share. We are still recording, right? Yeah, you should be able to share, Malek. Okay, I think it's coming up. Yep. And then Malek's discussion is Allah. Oh, is it me? Okay. I'm sorry. It's me. Yeah, please go ahead.
I think, Malik, you have to share the audio if you're trying to get the audio to the. So when you share your screen, there is an option. Probably there's an option called.
Yes,
All.
I guess I did share my audio. You don't hear it?
I don't think.
No, I didn't hear it either.
No. So are you
Okay,
walking through
let
the?
me try.
Oh,
Let me
I'm
try.
sorry. Sorry. Go ahead. I think you might be trying the video or the YouTube recording. If you have a PDF, you can walk through that as well, or a presentation.
My name is Malak Ahmadi, and now I will present my project. My project called Smart Requirements Classifier. This is what I will go over in my presentation. First, the problem and why it matters, the approach, dataset, modules used, applications, conclusion, and a simple demo. Start with my problem was that requirement.
I'm sorry to interrupt. Can you please increase your volume a little bit? Or is that the max? Okay. I think it's kind of low for me. I don't know if, about others.
It's a tad low for me too. I might just turn the volume up a bit more.
Okay. Go ahead, please.
I'm sorry because my computer doesn't have good audio.
No, this is better now, actually. I don't know what you did, but now it's pretty good.
Functional requirements are often mixed or unclear. Manual labeling takes time and can be inconsistent. Why it matters? Clear requirement improves software planning. Faster classification save effort and time. Clear labels help avoid mistakes in the project. Approach and dataset. I used natural language processing to classify requirements, trained a BERT module to classify each sentence as functional or non-functional requirement, compared them with a simple baseline module. My dataset was about 120, which is short requirement sentence. each labeled as function requirement or non-function requirement, and I cleaned the text and split the data into trained and test sets. Modules used. I used a BERT module to classify the requirement sentence. BERT helped understanding the meaning of the whole sentence, not just single words. It worked well for identifying whatever a sentence is functional requirement or non-functional requirement. And why BERT? Because it understands context. It gives better accuracy even with a simple data set. Result and limitation. The BERT modules reach about 90% accuracy. It was able to classify most sentences correctly, and the module performed better than simple methods. Limitation. The set was small. Only English sentences were used. Mixed sentences like function and non-function requirement together are harder to classify. Conclusion. I built a working AI tool for classifying requirement. BERT modules give better performance, and the system is simple, fast, and useful for software teams. Thank you for listening, and before any questions, I want to show you the interface I did. Well, this is the interface. Is a simple interface, and here you can write any sentence. For example, the system should allow users to create the system shall allow users to create an account. This should be function requirement. This is right. And the other sentence, for example, let's say the system should load within 2 seconds. This should be a function requirement. And that's it. Thank you for listening, and if you have any questions, let me know.
Okay, it's pretty cool. So basically, the the scope of the tool is to identify if it's a functional or non-functional requirement, and it's targeted towards software teams. Right,
Yes.
Malik? Okay,
Yes, you're right.
awesome. And then I think I might have seen this. So the data cleanup. Just curious, why is it manual when it comes to data cleanup? You're on mute. Malik, you're on mute.
Sorry, because first of all, I wrote the data myself, okay, and because it's small, so the manual cleaning was easier and faster, and I only needed to remove some noise and fix small things before training.
Okay. No problem. So basically, you chose to do it manual because of the data set limitations.
Yes, exactly.
Okay, no worries. And then just curious, if you didn't do it, that's fine. But how do you measure the performance?
Excuse me, what? I didn't hear.
How did you measure the performance?
I think you're still on mute,
Yes.
Malik.
Yeah.
Yes. I measure it by checking how many sentences the classifier were correct about. Like I give them a sentence or 10 sentences, and then I measure is this classification right or not.
Okay. But is there any metrics that you followed, like to capture the accuracy? That's fine. If you haven't done it, that's fine. No worries.
No, I didn't use any metrics.
Okay, that's fine. So basically, this is a tool to predict or classify functional or non-functional requirement and targeted for software teams. When you say software teams, I assume it's not just for the software developers. It might be applicable for the product owners and product managers too, right, Maulik?
Yes, not for software engineering only. You're
Okay,
right.
okay, awesome. Yeah. Thank you so much. I don't have any other questions.
Thank you.
Thanks.
Satish, if you don't mind, can I go next? I have a doctor's appointment, like 40 minutes. Extremely sorry, guys.
Okay. One second. I don't know who you are paired with.
Uh, I'll pair with David because me and David were supposed to join yesterday and
Perfect.
we couldn't join it yesterday. Yeah.
That
Um,
works.
okay, okay. Looks like it's Nahi, that's what I see it.
Yeah, I'm supposed to be next, but I can. It's totally good. If you need to go next, that's okay.
No, no, no.
Thanks, man. No,
I'm
thanks,
talking
man.
about the discussant. Yeah, I'll leave it to you.
Oh,
Yeah. No,
Oh,
no
okay.
worries. Yeah,
Yeah, feel free. Anybody can ask questions, guys. So
yeah.
yeah, it's good.
No worries. Go ahead, Vishwanath, please.
Yeah. Thank you. Thank you so much. Cool. So I'll quickly take you through my projects. Can you guys see my screen?
It's still loading. There we go. We see it
It's
now.
coming up. Yeah, we can see
Got
now.
it. Yeah, okay. So my project is about basically generating a product photo shoots because like this is one problem which a lot of small businesses face today because a lot of small businesses we spend like $100 to $300 per hour on like taking studio quality for product photos. So it's very difficult for small businesses where they have like more than 100 products which they have to sell online. They'll nearly have to spend nearly like $5,000 to just get the product photo shoots and so on. So I was aiming to build an app, a simple Streamlit app, which could basically it's like a four-stage pipeline where it takes product amateur photos from the phone. Like you could just take a picture of the product, and then we could use like a stable diffusion or like a control net model basically in the background to fine tune on the product features and the branding and so on. And then we could upscale it using like a upscaler, which we could have. So that's about the whole a product photo shoot. So let me quickly take you through the app. Um, and like we could talk more about what's happening in the behind the scenes. So this is a simple Streamlit app which I have built. It's you just have to upload a bunch of images. I just had like a bunch of trimmer images, which uh, you guys can still see the app, right? Like, is it still the PDF?
Yeah.
Yes,
yeah.
yes,
I
we
see
can
it.
see.
Got it. Got it. So we could upload like a product like you could upload like a lot of product images of that from different angles, and then you could give a different identifier for your particular product because we in the behind the scenes we are just using a dream booth model to uh, fine tune our model for this particular keyword, and then like product category can be wireless trimmer or whatever product photo shoots which you have. So once you train a model or like fine tune that model on based on the product images, I'm just going to give start training pipeline. So what's happening? I'll quickly take you through what's happening behind the scenes. Yeah. So initially I was training on like my headphones which I had. So like amateur product, you just take product photos from different angles. So what's happening? The pipelines triggers be removing all of the background images because we don't want the model to learn about the background features. We just want to learn about the product. So we remove using a Python library called remove background. We remove all of the background images, And then we use fine tune the model based on using dream boot technique, where we fine tune using that particular identifier, product identifier, and then we fine tune our stable diffusion Excel model. The better the model, the better the result. So if you notice, if you use the model is not able to capture all of the features of that particular product. So the next is where like we use a reference image to get like a canny map edge detection. So and then pass that along with the prompt saying that give it to me like in a better studio quality photo. So post canny map, you get like an image which is better and also has a brand of that particular product name and so on. At last, we are just going to use like a stable diffusion Excel upscaler to improve the resolution and so on. I'm going to currently the pre-processing is complete. The training is happening. I don't have a GPU in my system. It might take like an 40 minutes to run the entire pipeline. So I'm going to stop it. I'll quickly show how do you generate images from there. Yeah. So the next step, once the model is trained and saved in your system, you could basically come here, give whatever prompts you want. You wanted in wooden table, soft lighting, and so on. And you could also add negative prompts saying that these are the negative prompts which you want. And then you could, for the canny H map, you just select a reference image, whatever is here, and then you click on generate and upscale. Um, since the model is training right now, like this is one of my past results which I created. Basically, you could notice like we went from like the Yamashita images to like a basic images here. So but in terms of future scope, a lot of the Nano Banana Pro, if you know, if you guys have noticed recently, Gemini, Google has come up with Nano Banana Pro, where you could just upload an image and you could one shot prompt for all of the product images. So instead of fine tuning a model, we could just use like a better model to generate these images. But fine tuning is the best way to go about it because it will retain product images, it would retain all of the product features and the branding and so on. Uh, that's about my project. If there is any questions, feel free to ask.
Hey, great work. I was just sort of curious, so under the training photos there, right?
Mhm.
I guess, was there like a process that you used to determine what kind of training photos would give you the best results? It kind of seems like you're taking a photo of the same object. Um,
Yes.
yeah.
So I basically tested out saying like how many images is the best. At least I've seen like 10 to 5 to 10 images is the best. Taking the same product from different angles. So the more angles you capture about that particular product, the better your output photos will be. Does that answer the question?
Yes, absolutely.
Yeah.
Okay, cool. And then just to be super clear, like those are being fine-tuned on the on the model, and then you're providing the reference photo as like a separate request to get your output.
Yes,
Yeah.
so if you notice here, we are using reference images for like the what is for the edge detection on the map I'm just using a reference photo here. This will be passed through the control net canny map to get that shape and like the product features and so on. So yeah.
Okay, excellent. Great work.
Yeah. So in terms of evaluation, if you notice I've used two things. One is clip score and like NOIQ. I forgot the full form, but it basically measures two things. One is identity and quality of that. Identity is like how the product is uh, generated and if it matches with the source image, and like quality is like the whether it does it look like a real image and so on. Yeah, that's about it.
Awesome. Really good stuff, Vishwanath. Thank you.
Yeah, cool. Thanks, guys.
So who wants to go next? Nahian?
Seems that way. Alrighty. Where are we? Right. Okay. Can we see this all properly?
Yes.
Okay, sounds good. All right. Hey guys, my name is Nahian. I did a project, a tiny reproductions project on reproducing convex modernization techniques. And the subtitle is When ImageNet Innovations Fail on Small Scale Data. So, just for a little bit of background on my project, the original paper for this was called A ConvNet for the 2020s. Essentially, the central question that they're trying to answer is, can CNNs match vision transformers without attention mechanisms? So, they're trying to do essentially their approach was that they were going to do a bunch of systemic modernization processes on a CNN and see if they could match like how close they could get to vision transformers and like residual networks if they could beat them. And the image set that they used was ImageNet. Now ImageNet is like pretty large. They were obviously working on like a very large scale, so a lot of this was like scaling it down by almost like to 10%. So they showed at least that they got 6% improvement in classify 6 to 15% actually is on the upper range in classification performance improvement on ImageNet using these various techniques. So let me break down some of these techniques real quick. So first was Adam using Adam W as opposed to stochastic gradient descent and doing 300 epochs. They also did some like macro architectural designs where they were like playing around with the stage ratio. So they were this essentially changes how the blocks are distributed across the different stages of the model, and then like also playing around with the like down sampling that happens at the beginning of these blocks. Then uh, like more depth in the convolutions, and then also the main like architectural, I think, interesting interest was the inverted bottleneck, which just kind of like the if you guys remember from class expansion and contraction, this is the one of the steps that they added. They increased the kernel size, and then they changed ReLU to GeLU, did layer norm and layer scale instead of batch norm. Um, so what this boils down to is my experiment is do these architectural improvements apply to smaller data sets, hence a tiny reproduction. So I recreated convex via code, so doing it on ResNet 50, but the changes are a little bit different. So I tested it on SciFar 100 to see if the innovations would transfer to small scale data sets, both in like image size and in like image quantity. Um, Really, unfortunately, due to just like constraint, like hardware constraints, I could not do 300 epochs. Um, and also test every single like ablation study that I'd want to do. Um, and uh, the other changes were smaller channels, and um, like essentially what I'm trying to do is isolate the architectural changes as opposed to something like data pre-processing. The other thing that the paper mentioned is that were like specific techniques for image pre-processing, so mix up, cut mix, and rand augment that I did not do, at least in this iteration. So all that being said, like I ran this 5 times on each, trained 5 times, and Convenext and ResNet Convenext scored 52.5% and ResNet 18 did 67.3%. Um, ResNet 18 being like the original model that we modernized on. So like what happened? So after a little bit of digging, I saw that one, like the first issue was kernel size. The original paper used 7 by 7 kernels, which I followed. But the original ImageNet is much, much larger. And I had to scale that as like a percentage of the ratio. So I reduced it back down to 3.3% or 3 by 3, and that increased accuracy a bit. The next one was adding more stochastic or adding drop paths. So this is like randomly skipping a block, um, and like increasing the probability of skipping a block, which basically helps with regularization, helps with reducing overfitting. Okay, so the that seemed like that was the dominant factor, but I like overlooked something pretty important, which was like just raw parameter count. ResNet 18, at least how I had implemented it with the dimensions, had like significantly more parameters. Now it's like not quite um, does not how do I say it? Like the 50 like the 35% increase in the number of parameters like does not or your 34% fewer parameters shouldn't have this much like offset, right? So I increased it and trained it again 5 times, and the average accuracy was like 60.3%. Still underperforming, but quite a bit better. So here the conclusion. Like reproducing this paper, it was like pretty tough as a tiny reproduction. Scaling the model and like trying to get the hyperparameters to match as like scale as opposed to just like, hey, we're using a 7 by 7 kernel or like these dimensions. That's I've like concluded that does not like really get you very far. Um, Really, what you need to do is like look at each of these different like architectural improvements that you might be able to make on your model to increase accuracy and apply it directly to the data set that you're working on. If I were to do this again, I would redo this with the image pre-processing that the original paper had done. I would like boost it up to 300 epochs, but it seems like the loss was catching up, and then also do some sort of learning rate scheduling or warm up. Uh, Please let me know. But yeah, that's for my project. Does anyone have any questions?
So I can go. This is Raj. So I think I don't know if you use this, but Google Colab has a GPU. Kept even the free version has a GPU and a TPU option. So when I was working on this classes assignments or the project, and that helped me quite a bit. Just wanted to add that.
Yeah, yeah. So I'd actually used that, which is I think that's super interesting. Really, and I was not able to get past like I originally tried it with 300 epochs, right? Um, and I was not able to keep the connection, right? So then I spent some money, and then even that, it was basically taking way too long to train. I have a computer with a dedicated GPU, and that was also taking about like, at least on like a consumer grade GPU, is taking about, almost a day. Um, so I think there's probably something that I could have optimized there. Any other questions?
I don't have a question, Nahian. This is pretty cool, pretty intense from a technical depth standpoint. I really like the way you got back to the parameter count, which is kind of a critical stop point in your junction.
Yeah.
So no, that's pretty cool. Thank you.
Yeah, thank you. I think it's really interesting because I feel like it's very easy to get tunnel visioned on one problem, especially, these are very complicated networks with a lot of like higher order interactions that uh, and I feel like I got tunnel vision onto, modernizing one step and not like taking a more holistic approach, looking at each of the different layers and how they're interacting. Um, so I guess it's good experience for the future.
Absolutely, it's part of the learning process.
All right. Well, If no one has any other questions, I'll give you back the floor. Thank you all for your time.
Thank you. So who's next?
I think I'm next.
Oh, please go ahead.
Let me know if you can see my screen.
Yep, I see it.
Yes.
All right, cool. 1 second. All right. All right. Hello, everyone. This is my presentation on an explainable on-device spam filter. So most spam filters today run on cloud servers that scan private emails, and while they work well, they raise serious privacy concerns and sometimes mark real messages as spam. Local filters avoid that, but lack context and personalization. My goal was to create um, a privacy-preserving explainable spam filter that runs directly on user's device, restoring privacy and trust while still being accurate and transparent. This approach also aligns with data protection laws like GDPR, which discourage remote content scanning. The design priorities were to keep it fast, explainable, and fully local, processing each email in under 4 milliseconds. In the system pipeline, incoming emails are first parsed for authentication headers like SPF, DKIM, DMARC. Next, behavioral and content-based features such as sender history and link counts are extracted. These features feed into calibrated logistic regression models, which outputs a trust score and a short explanation showing why the email was classified that way. This modular design allows real-time privacy-first filtering without any cloud dependency. So this is kind of like the flowchart of how the spam filter operates. This model uses 12 interpretable features divided into 3 categories. Authentication features like SPF, DKIM, and DMARC pass-fail checks. Behavioral features such as whether the sender is in the address book or part of an ongoing thread. And heuristic features such as the number of links, suspicious domains, and the capitalization ratio in the subject line. All of these are lightweight and human understandable, making the system transparent and efficient. I chose logistic regression because it's fast, interpretable, and well suited for structured data. Then I applied isotonic regression calibration so that the predicted trust scores align closely with real probabilities. And my performance goals were precision around or greater or equal to 0.88, recall around 0.9, and latency less than 4 milliseconds per email. And the prototype met all of these targets. Compared with a simple keyword-based filter, this system reduced false positives by around 33%. Precision improved to 0.89, recall to 0.91 with an F1 score of 0.9, and ROC AUC of 0.95. The most predictive factors were authentication checks and sender history, while suspicious domains and excessive links were strong negative indicators. After calibration, the decision threshold stayed the same across different data sets. Here's what explainability looks like in practice. Each email receives a trust score and a short reason for its classification. For example, an email from your boss with a valid SPF and DKIM gets a 0.97 trust score. A random address like we have here, lottery at xyz.zip, fails all authentication and gets a 0.12. Users can view these feature influences and adjust filters manually, making the system both transparent and user controlled. So to wrap this up, this project reduced false positives by a third, achieved real-time latency around 3 milliseconds, and proved that privacy and explainability can work together in machine learning spam detection. And this prototype runs fully offline, delivers clear feature explanations, and shows that real-time spam filtering can be both private and effective. And now I'll show you a quick demo of how it runs. So here I have this code that has some spam emails, like kind of like just sampled into it. And I have some so ham emails are just the opposite of spam emails. They're legit emails. So I have a couple of both here, and that's what I'm using as like my data set just for this sample run. So if I run the code here, You can see the results of everything right here. So the model trains on 8 emails, as I showed you, four legitimate and four spam. And you can see that it achieves perfect precision and recall on this very small sample size. But it was tested over 1,000 email sample size. And below that are the top feature influences. So positive weights like SPF, DKIM, and DMARC passing all raise a trust score, and those indicate a legitimate email. And then negative weights such as suspicious domains, too many links, or all caps subjects lower the trust score. And those are classic spam signals. So we finally tested with a real example from alerts at purdue.edu, and it passes all authentication checks. So the predicted spam probability is just 0.37, which means it classifies as a ham email, which is a legitimate message. And hopefully this demo is able to show that the model is accurate and interpretable, and runs entirely offline, which is the main goal of this project. So thank you for listening to my presentation, and I'll take any questions you guys have right now.
Hey, this was really cool. I'm just curious about the model you use itself and kind of the expectations you have for hardware if you want to be running it locally.
Yeah, so I kind of worked on like a similar spam filtering project when I was taking 495 last semester, and so I kind of knew what spam filtering was, but it wasn't really running locally on offline or anything. It was kind of using a public server with like API keys and whatnot. So that was where the main motivation was to kind of make this run offline entirely on your own, so that you don't need internet dependency and stuff like that to run software like this. And then for training it, I kind of had an existing training model from what we worked on in the past, but again, I wanted to make it a bit more robust and kind of get rid of false positives. So I kind of just um, ran with more sample sizes, different types of emails. When we were testing it before, we were running both our own created emails, and we would just download existing like spam type of email templates. And a lot of times when you download it from the same batch and stuff like that, there'd be a lot of common similarities between those emails. Maybe like the type of email URL address and stuff like that will have a little bit of similarities. So this time I went around and got a bunch of emailed samples from a bunch of different sources to kind of make sure that the sample size is truly representative of as much of a large sample as or a large population as possible. So once I tested it with a much bigger sample size, I was able to get better results, and I was able to train this model to expand its horizons and basically get used to seeing a much bigger sample size. So once I did that, that's what really helped improve a lot of my scores, and is how I was able to get like the scores that I showed in the slideshow.
Okay, very cool, man. Thanks for sharing.
Yeah, thank you.
David, sorry, Jay, I just had one question regarding is there a reason you went for choosing a metric for precision or recall? So,
Sorry, I couldn't really understand your question.
Your voice is really breaking.
Can you just hear me now?
Yeah,
It's
it's still kind of
muffled.
hard.
Yeah, go ahead. Jay, I do have a question, but I'll wait for Vishwanath to see
Okay,
if he can come back.
sure, sure.
Just asking if there is optimizing precision or recall. You know?
I'm sorry, I still have a little bit of trouble understanding the question.
Just in the interest of time, maybe I'll go next. Really quick question, Jay. Not a question. So please correct me if this isn't relevant to this particular topic. So what is the commercial use case for this one? Like for example, not for example, Outlook, Gmail, everybody
Yeah.
have their own filtering. Even the behavioral analytics are coming into play for the predictions, right? So for this one, what is a commercial use case? This is more for my understanding than a question. Again, if this is irrelevant,
Yeah.
so please move on.
Yeah, no worries. So yeah, a lot of these major mail services do have their own spam filtering. And I guess like when we had tested it as a group in our past project, we had noticed that there are times that even if you have a Gmail account, you'll still get spam emails all the time and stuff like that. So obviously, it's not doing a fully robust job of um, making sure that all the spam is filtered. Like for example, even I can go through my inbox right now and find emails that are from fake addresses and whatnot, and Gmail will still let them through. Even with like the Purdue emails, they'll still get phishing emails that get through, and you can still receive it in your inbox. So obviously, as big as these are, you're still getting spam emails. And I kind of obviously it's going to be hard to compete with the kind of technology that they have and try to make a better model. But I kind of wanted to see if I could just find ways that or if I can just find things that I can do that maybe improve the accuracy, at least on my end. Maybe not to the point where it's robust enough that I can apply this on my own inboxes and whatnot, but maybe I can kind of just try to find keywords or patterns that I can identify that I can use on my own, that I can maybe consider using in the future when trying to filter out a lot of spam. Because a lot of the emails I get right now that are coming through still as spam will have the same kind of capitalization patterns or the same type of subject matter and a lot of those things. So I was thinking maybe if I try to train a model based on those kind of repetitions and characteristics, then maybe I can at least do a slightly better job of filtering spam, at least the spam that I'm getting. So that was my motivation behind it.
Okay, okay, awesome. Yeah, that makes sense. Thanks, Jay.
Yeah, thank you.
So it looks like there is a chat.
Okay, I think I'm next.
Oh, I'm sorry, Raj. Looks like there's a chat from a question from Vishwanath for Jay, maybe. Looks like it's for Jay. Is there a reason you chose precision or recall to optimize the metric?
Not necessarily. I think I was just researching a bunch of different methods, and those were two of the best suited ones. I went through a bunch of different um, training models and stuff like that, and different metrics, and those were just the two that had the best impacts on my precision and recall scores. So that's why I went with those.
Vishwanath, hope that answers your question. Oh, great. Sorry, Raj. Please go ahead.
No, I was just want to make sure that I'm the next guy. So
We can see your screen. We couldn't hear you, Raj.
can you hear me?
Yes, yes.
Okay, I don't know what happened then, but yeah. So my topic is how to detect in a scaled way crop stresses like with climate change and a lot of uncertainties. How does farmers decide you know a which part of the land is best suited for what type of vegetation, and then b how to get the yield, maximize the yield. And just as a background, I've worked in my work side. I had a customer for almost like 2-3 years where we help them. It's like a aggregation of co-ops, agricultural co-ops, and build out. I think the second largest ag company in US. So the company, it was Land O'Lakes actually. So they have you know uh, business units in agriculture, in dairy, and other areas as well. Um, so working with them, we have worked with farmers where we brought in sensors, we brought in drones, we brought in satellite images, and tried to kind of help create micro, you know uh, a section of their farm, in a very limited way and provide this data to them. So this actually, after those series of things we did with them, um, in my company, we started to think about how do we do it at scale, because it's the world is very vast, and agriculture, as you know, is all spread out all over, and also in remote places mostly. So what this project is about is how we can use um satellite images, which are open source, so you can get these from different sources. uh, Even like AWS has open data repositories, Microsoft has, Google has them in Kaggle. So get those data, and then take the imageries, and then there is something called normalized difference vegetation index, which is using two spectral bands, which is near infrared light and red light. You know, you kind of create an index, and I'm not going to go too deep into how this index is created, but it's kind of if it's between 0 and 1. If it is close to 1, it means that patch of land which is covered by that image has healthy vegetation. And as it goes to 0, it means it's kind of going down. So what I did end up is first take the satellite data and then convert it into into a time series. So I took the satellite data in a time series format, so different point of time for a period of time. Of course, in a very subset of the data was my scope of work, because again, limited by time and compute. And then converted it into a binary format. And the technique what we were trying to test out was, can I create using this data only, and provide a good enough forecasting model which can be used in every location as possible. So what I ended up doing was use two layers in my models. So one was this temporal mask encoder, TMAE, uh, and the other one was a weak supervision, and which predicts from there whether it's a stress or no stress. And what if I kind of little bit double click on this, what this does is you have these satellite images, converting them into through that NDVI uh, computation, you convert them into a time series binary format. And then this encoder, it the way it trains it is, it suppresses like 60, 50, 70% randomly from the input, and let the decoder predict it. And then you kind of compare it with the actuals to see if it's within that acceptable loss range. So how accurate or closely it's coming to. So that's how, without manually tagging, without needing other devices, we were trying to kind of create this model. And then when we compared this, we compared it with the different other studies which were done. And again, I did not do the other studies part because limitation of time, but our ones came in, like the F1 score, AUROC score came in actually quite better. And I mean, the prediction process was much quicker. It would give us like almost like 11 days of lead time before the actual damage to the crops could happen. So that's my, my project. And the way I structured it, I kind of created a modular structure with which I have already zipped and put it in the the project submission. So the data pipeline, which was the data synthetic data creation process, and then uh, there is this weak labeling, and then this temporal you know Python files, which does um, the process of you know um, training the models, and of course it's run by these training and then fine tuning Python, and then the evaluation gives you that F1 and ROIC, AU score, which was run through batch. Again, I like I was mentioning to somebody that um, I used Google Colab, so I also submitted the Colab, uh, the control Python script. So, in conclusion, what we were trying to do was provide a sensor-free crop monitoring approach. Do it, give a confidence level of these models good enough where the quality does not get sacrificed, and then without having to manually label the images. So it was self-learning, and it's it could cover diverse geographic regions. That was kind of the goal of the project, and I'll take questions.
Great project.
Yeah, probably I'll if it's okay, I can ask one or two questions, Raj.
Sure.
Yeah, no, this is pretty awesome project, and it's an important topic to be researched. So thank you for doing this one. From a threshold standpoint, just curious how you were able to plan for the thresholds, either for labeling or in the pipeline. Just curious on that aspect.
So I was going against, like I said, when we were I did this with like multiple sources in the past. So I had some of these data sets already with me.
Okay.
So I was comparing it with that effort which I had done long back. Actually, there's a team called Farm Beats. It's a team in our company in Microsoft, where we were engaged there as part of that team, and then there has been some more work done between then and now, and this was like one part of it I was trying to test out through this project.
Awesome, awesome. Yeah, that makes sense. This is more maybe my ignorance, Raj. So help me understand. So when you say stress-free, sensor-free, if there is a sensor, is it a problem for these kind of activities? What does the
It's cost.
sensor-free
It's a
consider?
cost, like
Oh, cost. Okay, okay.
getting the soil moisture, then capturing the temperature, throughout a period of time, right?
Okay.
Then feeding those data, streaming those data, capturing those data, in remote areas. Those are like very, challenging. They don't
Oh,
have proper, Wi-Fi. When you're covering like large sections, I mean, even if you have Wi-Fi, it does not cover the entirety of the acreage of the farmer. So there are like significant scaling challenges. So we kind of model it in traditional ways. We model it in micro segments, and then try to generalize it. That
okay.
yeah.
Okay, totally makes sense. Yeah, sorry, I didn't get that in the first place. No, this totally makes sense. Thank you, Raj.
Hey, Raj, I had another question, and maybe you might have talked about this, but if if this system is applied across different geographical regions, would the same model generalize, or would it need retraining and adaptation for different conditions?
It should generalize because I was showing you that NDVI index, right? So it reads the the infrared and red uh, colors from those images, and there is a an index has already been defined which maps out to you know the state of the soil there. So even if I am, trying to do this in, let's say, somewhere in Phoenix, Arizona, or Texas, or Wisconsin versus Iowa, I mean, that index is standardized, so it can
Okay,
be generalized anywhere.
got it. All right, thank you.
All right, then we'll move to the next, Satish.
Awesome. Yeah, thank you, Raj. Think we're left with David. I think you're the last.
Okay. Hey guys, thanks for sticking around. I'll try to keep this brief because I know we're exceeding our time.
Oh, no worries,
So,
no worries. Yeah, take your time.
okay. Share my window. All right. Give a second. Let me know if you guys can see.
Not yet, David.
Not yet, not yet. Okay, hold on. Let me try something different. No, share window. Okay. Perfect. Okay. Hey guys, I'm David. I'm doing a tidy reproductions project on a paper called The Illusion of Equivalence, which compares full fine-tuning to low-rank adaptation. So I'm investigating muon's impact on low-rank adapter intruder dimensions and forgetting. So quick background, low-rank adaptation is a widely used strategy for parameter-efficient fine-tuning. Recent works, such as the paper I mentioned, have shown that LoRa is not equivalent to full fine-tuning, both in training dynamics and performance, specifically in the continual learning space. The paper finds that LoRa introduces this concept called intruder dimensions, which are high-magnitude singular vectors that are orthogonal to the weights pertaining to the pre-trained weights. And they found that these intruder dimensions correlate with catastrophic forgetting, in which a model forgets data that has already been trained on when learning tasks in a sequential manner. So I propose, can we fix this problem through maybe a new optimizer, focusing on the geometry of learning? So quickly, what are intruder dimensions? These are these large singular vectors that are orthogonal to pre-trained weights, and they are found to be created during low-rank training. They matter because they act as somewhat of an optimization shortcut that LoRa has kind of implicitly found, but of course they found to also cause catastrophic forgetting. So I propose to use something called the muon optimizer. The principal idea behind muon is that it orthogonalizes the momentum updates using an algorithm called the Newton-Scholz algorithm. And this is an approximate algorithm that is able to orthogonalize the momentum buffer. And I kind of had this hypothesis that this spectral regularization will suppress the intruder dimensions. So the experimental setup I followed is I took a transformer model, a small Roberta base model, and I tagged on some low rank adapters. I swept across different ranks for my LoRa adapters, starting at 8, 16, 64, and 512. And I sequentially trained 5 language understanding tasks, starting with MLI. Sorry, this isn't rendering correctly, but MNLI, QQP, SST2, SIQA, Winter Grande, and also Fever. These are just typical language understanding tasks used in literature. The metrics that I care about here is basically the number of these intruder dimensions. And the way you can analyze this is you can break down individual weight layers using singular vector decomposition. And then I track accuracy of MNLI over the course of additional task training. I also monitor the pre-training forgetting using something called pseudo-loss. Pseudo-loss is all I'm doing is I'm looking at basically the perplexity of the model on open web text. And open web text is one of the data sets used to pre-train Roberta base. And then I average the forgetting. And then I do this comparison between AtomW and muon. So a quick little figure from my paper. You can imagine just a line going down between these two right here. On the left here, we have randomly selected this is actually all of the weights, all of the weight matrices for Roberta base. And in this case, I was using rank 8 LoRa adapters with AtomW, training it on MNLI. And I again used this SVD-based intruder dimension calculator. And I found that there are a total of 209 intruder dimensions with AtomW. I performed the same fine-tuning task on MNLI, but this time using muon, and I did find that muon actually has a lower number of intruder dimensions. Again, ISO rank as well. Secondly, here we have also found that there's a rank-dependent behavior that comes through with this LoRa thing. Sorry, this figure, I think this might be the incorrect figure, but anyway, what I'm looking at here is I'm looking at LoRa at rank 16, 64, and 512 being trained using AtomW, muon across, initial MNLI and final MNLI. So what we start here is like when we first start, our first task I train the model on is MNLI, and then I train on the additional tasks that I mentioned earlier. And I observe the change in performance on MNLI after each new training session. And then I monitor approximately the average forgetting. And unfortunately, I didn't really find any interesting trend. I actually found that muon will sometimes underperform AtomW in the sense where muon will actually degrade compared to AtomW will sometimes have improvements. But I did find that there is a trend in which when you go into higher ranks, I find muon to be a more stable training strategy or optimizer strategy. So there's less change from the initial task to the final task accuracy-wise. And I did have I will mention this later, but there was an issue with my rank 64 training in which I had training instabilities, and I was unfortunately not able to record results from muon. Okay, this is a more informative graph here. This is the continual learning trajectory. So each node you see here is task accuracy for MNLI. So I know I'm listing additional tasks, but each node represents the accuracy for MNLI after training on an additional task. And we actually see an interesting thing is AtomW, or the model trained with an AtomW optimizer, actually increases accuracy. I will at least mention that this did not hold for other tasks because I also performed a deeper analysis in the paper where I observed task accuracy for say QQP, and then I trained on SST, SIQA, etc. And I found it was not also increasing accuracy. In fact, they would drop usually. But the key trend here is to observe is that muon provides a much more stable training trajectory in the continual learning regime compared to AtomW. Now, sometimes it can be good to have a high variance, but sometimes you don't always want that. And so kind of the key thing here that I'm finding is that higher ranks do enable this spectral regularization hypothesis that I proposed earlier. This is monitoring pre-training loss, in which I'm monitoring the perplexity of Roberta base, and again, Roberta trained on each sequential task, monitoring how much it's been losing its knowledge base. And I find that, it's approximately the same. In fact, actually, AtomW seems to even improve while muon is decreasing. So there are no interesting trends that I'm able to observe here. So a quick discussion. Why is muon able to provide a more stable training trajectory at higher ranks? So first off, AtomW uses a coordinate-wise normalization strategy. which can lead to rapid growth in gradient directions, because coordinate-wise just basically means each parameter is optimized independently. Again, this can lead to rapid growth in many different gradient directions, along with spiky singular values, which we saw with the higher intruder dimension count. Muon, however, orthogonalizes the momentum value, and this leads to a flattened gradient spectrum, which we found can prevent orthogonal components and essentially provide uniform perturbation. And kind of the main thing here is that what I did observe is that higher ranks can give more freedom for this spectral regularization strategy, which leads to a higher training stability. I want to address just a few limitations I encountered and maybe some directions for future work. First off, like I said earlier, I did encounter training instability in which my rank 64 training run failed. And due to some hardware limitations with my lab, I was unable to rerun those. I only looked at Roberta base, which is a much smaller encoder-decoder model. The paper did look at Llama 2 models, but due to hardware limitations, I only stuck to Roberta models. You could do a much higher and much more in-depth hyperparameter tuning. You could look at, maybe even more LoRa ranks. You could play with learning rates, all of your typical hyperparameters that you would encounter in a deep learning project. You could also do an analysis on. And again, yeah, scaling up to more interesting model sizes would be maybe an interesting direction. Testing on longer continual learning sequences, maybe. This was rather small, language understanding tasks, but there may be some more interesting properties that arise when you look at longer time horizon or longer horizon sequential tasks. And again, yeah, forming a theory behind what I'm observing. This is very empirically driven, this project, but it would be very interesting to develop a more formal theory behind this observation. And so kind of my conclusion that I have right now is that, optimizer geometry is critical for ensuring that you have a stable fine-tuning environment, especially if you're going to be considering sequential fine-tuning. And, especially at these higher ranks, or maybe even going into full fine-tuning, spectral optimization may be optimal for training stability compared to coordinate-wise optimization. And I do think that optimizer choice, given my results, does provide an implicit regularization for knowledge forgetting. Oh, and this is pretty cool. This, to my knowledge, this was the first study for muon in a continual learning setup. Muon has gained a lot of attention over the summer as a new optimizer used in pre-training setups for large language models. I do think it needs more work, but I do believe that given my early initial results, intruder suppression via spectral regularization is a potential outcome and could be very useful for training stability. And as I saw, I was only seeing this occur with higher ranks. So I do have to say that this is a rank-dependent behavior as of now. Thank you very much, guys. I'd like to take any questions you may have now.
Very cool. That's funny. I almost did this paper. So you
Oh,
did.
really? Okay.
Yeah. I read this paper too, and I was almost did this one. So, I guess what are some of the things that, at least from your observation, that you saw that, like, why focus on fine tuning again? Is it just due to computational limitations, or?
Yeah, that's a great, really good question. It was the initial analysis. I actually wanted to make this a bigger project, but just due to time constraints, I had to turn it into a tiny reproductions. It would have been really cool to do pre-training. Is that what you're suggesting? Like looking at it as a pre-train? Yeah, good question. It's simply, yeah, a resource limitation thing. It may be really interesting to see what happens in pre-training. You'd get probably a much longer, probably just fidelity with much more training steps. You'd see initialization. You basically start from weight initialization. So I honestly don't know what would happen. I was only seeing this, what do you call it? Stabilization at higher ranks. So you may have a good point. Looking at pre-training, wherever all the weights are being updated, you may see this higher degree of regularization.
Yeah, it's like it's interesting because I feel like if you I wonder like, how quick, like how much faster it might be, like how this might affect training time, like if you were to, start with some
Oh,
pre.
it's
Yeah.
sure. It's definitely, I mean, kind of the main conclusion I'm seeing right now is Muon is a faster optimizer in terms of training steps. I don't know actual walk lock time, but uh, yeah, the main impetus is that why I picked this project is Muon has been found to be a faster optimizer in terms of training steps.
Cool. Awesome. Thanks for this project. I learned a lot.
Cool. Thank you, man. I appreciate that. Any other questions, or if not, I can conclude.
I don't have any other questions. Thank you, David.
Awesome.
Because
Thank
that's
you,
my
guys.
questions. I think we are good. Thanks, everyone. You guys have a great weekend. So what I'll do is I'll stop the recording. I'll upload it somewhere and then share it, like update the spreadsheet as well as share the link with you all in a few minutes.
Right.
Perfect.
Okay.
Thanks,
Okay.
Andy.
All right.
And
Thanks,
just
everyone.
Thank you.
one question for clarification. In the grade scope, when we're putting the order of the projects, are we going through the updated order with Vishwanath going second or third-ish, or should we go on the order listed on the Excel sheet?
Do listed. I did listed.
Okay.
Yeah.
Okay. Cool. And which session were we again? Presentation session?
3.
This is
It's
online
like
acceptance.
3, I think.
So
Yeah,
three?
online
Okay.
exception 3. Yeah.
Okay. Got it. All right. Thank you, guys.
All right.
All right. Thank you,
Thanks,
guys. Thank you
everyone.
very much,
Yeah.
Satish, for
All right.
hosting
No
this.
problem.
Yeah.
Thank you. Bye.
Bye-bye.
You guys around.
Thank you.